polynomial function. Now, Jonathan, I can recall you actually, from the handout, I think you told us what a p of x polynomial function looks like. It's all drawn out.
Yep.
And we looked at the degree, leading coefficient, constant. We have that, right?
Yes.
We have that done. Okay, with that said though, before we jump into it quickly, I'll point out something here. Yeah, it's right here. You have to know how to sketch a polynomial function. You need to know how to sketch. You want to take some time to look at that. Now, since I've mentioned sketch, please tell me, if you saw this, I'm just creating one right quickly here, standing here. Is that a polynomial function? Yes, three terms, trinomial. It just so happens it's a what? Quadratic. And that's what you were quizzed on or on the exam. You can sketch it in no time. Either take the time to put in the vertex form, complete the square, or using ABB over 2A, you've already seen that. But that is a polynomial. Number two, another example right quick before I jump to it, let's call this P of X. Myself, I think I went through some of these last week. That's a cubic. And I think even from last week in the discussion we had, we could sketch that. Right, factor it, find some critical numbers and test. Is that true, guys? Use sign analysis. We did that. Guys, these are types of polynomial functions we're responsible for to sketch. And besides sketching, let me leave that. Part B, I better mention this word. If they ask you to find the zeros, which I'll be asking you to do for me, if they ask you to find the zeros, what do they correspond with?
The x-intercepts.
The x-intercepts. On the graph, this is the same as the x-intercept, so that word zeros, find the answers. C, all this about polynomial function. I have mentioned here in behavior. How's my graph behaving on the end? Now, guys, I think I had it written out like this. Find the limit, and I'll abbreviate the word limit. As you make x get large, written like this, x is approaching infinity, of my function, and of course then you determine what that is, answer is. And then that will help you see what's happening on the end. I can have rewrite this as limit, as x is approaching negative infinity on the other end, polynomial function, then determine what's happening, and that will help me to give sketch, or a start on the sketch, at least on the ends. And we'll look at that today. Letter D, here on this side, it's what we have already. Yeah, cross touch. Just a recap. Now guys, if anyone remember anything about cross touch?
It has to do with the multiplicity of the intercept, right?
Okay, I meant, the word multiplicity.
If it's an odd multiplicity, it crosses the x-intercept, and if it's an even, it just touches the x-intercept.
Okay, we're gonna take all that together. Cross touch, Eric described that. Multiplicity, describe that. All these have something to do with the polynomial function. Eric, go for it.
I just have a question. When we were graphing these functions last week, we were using sign analysis.
I use not.
When I was graphing them in the book, it just told me to use the multiplicity.
That's what we're going to do today.
Does that negate sign analysis?
No, not at all. Not at all. You can still use sign analysis. The third focus on chapter 3 there is using this multiplicity, cross touch, in behavior. Then once you start using that.
Does using multiplicity allow us to not use sign analysis?
Oh yeah, you can still. Using the multiplicity?
Yeah.
Yeah, you don't have to use sign analysis.
Okay.
Unless you're asked to do it. Guys, also, please remind me what is meant by that and what is meant by this. A polynomial function greater than 0, a polynomial function less than 0.
Above the graph.
Above and below. In fact, I think this is where I was using my sign analysis last week.
Yeah.
Okay? That's all it means. Let's see if I can do the part here. Cross touch, there we go, oh yes. And then letter G, I thought I would mention this again, there might be a max, or it could be a min, value on that sketch. Okay? Now, if I end there with what I think is pretty good recap so far. The max min, guys, if I go back to this one, this is a polynomial function. It's one we work with a lot. We're tested on this. Quadratic. Can I find precisely where the max or min is on this? Well, of course, I ask you to do a few of those on the test. Right? Without graphing, you remember how to do this? How'd you do that on the test last Friday? When I said without graphing, name the max or min.
Oh, vertex.
Yeah, negative b over 2a.
Yep.
And I know some of my students like that 4ac minus b squared over 4a. They use that. Absolutely. That's what we're talking about here, max or min. Now you say, Professor, how about one like this? There could be max and min on this one also. But we're not going to be able to find them here in math 2. Not for a cubic. We're not going to be able to find them. Anna and Bart could, but we can't do it here. Okay, but they do exist. So guys, that's a little recap, but please now, I did that quickly before I came in. A, B, C, D, E, F, G. Anyone think of anything else? Before I jump into maybe and start this and.
Oh, the y-intercept.
Oh, the y-intercept. Okay, I'll throw it in. And no matter what it is, we know how to find the y-intercept. We just take p of what? 0?
Yeah.
Replace all the x's by 0. We got the y-intercept.
Or I guess the maximum min is part of the turning points, right?
There you go, the turning points. That's what will come up on the handout.
Oh, yeah.
Turning points. You know what? Jonathan, thank you. Right here, before I jump into that handout. Chapter 3 identifies these as turning points on your graph. Okay, and those turning points could be a max or a min. Yes, Leo.
Sorry, could you just quickly refresh me on cross touch?
On the cross touch, Jonathan did a beautiful job. Was it Jonathan?
That was
Eric. He, remind Leo, cross touch.
So when you have your x-intercepts, each one of them has a multiplicity of 1 through whatever, and if it's an odd number multiplicity, it crosses the x-intercept. If it's an even, it just touches it.
Thank you.
There you go. Perfectly said. Okay, guys. So with all that said, here we go. I have in my notes here, it may not be on that handout there yet. Part 2 says, let's do a sketch. So all of a sudden, part 2, sketch. And I brought this one in. P of x, P for polynomial, and it looks like this. 4x cubed plus 10x squared. And then I threw in also besides that, subtract 4x, subtract 10. Now let me step back and take a close look at it. Make sure it's all copied down correctly. Just like it is. As a polynomial function, has 4 terms. The degree, the highest exponent is? 3. Called cubic. Now, I can't recall last week, did I sketch this one?
No.
I've sketched so many. I don't think I've sketched this one, have I? Okay, so we're gonna sketch this one. Guys, I'd like to see what the sketch looks like, and I may rely upon some of this recap here for my support here. But what would you suggest for a start that you might want to do, if you can, that may help you to get there? Factor. Now you said, Professor, how can I factor this? It's got 4 terms. Well, I could try this method of grouping, which sometimes works and sometimes it doesn't. Group by pairs. Now if I group, what can I do in the first grouping? I can take out a common factor of, help me out.
X squared.
Well, more than that.
X.
2x squared. If I do, I'm going to be left with, guys, help me out here. 2x is it? Plus
Minus
5. And let me step back and look at it. Is that true? Now what can I do in the last grouping, which sometimes works out? Can I take out something there? Can I take out a little bit more?
4.
I could try -2. And let's see why I might have decided to take out -2. Be very careful. Well, I end up with 2x plus 5. I'm careful. Down there, it if I pull out a -2, which is the best case ever, that's when you smile. Because now you have these two matching up. And therefore, they are a common factor at this point. So take that out as a common factor, 2x plus 5. And guys, left over the first term will be 2x squared on the end minus 2. Now, is there any additional work I could do before I jump into sketching?
Set them to 0.
Something else?
Factor the whole.
I'll come back further. This, I can take out a 2. And guys, if I take out a 2 here, x squared minus 1, will that factor further by difference of squares?
Yeah, x plus 1, x minus 1.
There you go. Now let me put all this together. So p of x at this point now looks like this. I got a 2x plus 5 out front. I've got a 2 here, which I may just go and place out front also. And then I've got x minus 1, x plus 1. That's what I have. I prefer, still, we will not confuse ourselves, this 2, we usually place that number out front. And that's a little better. And there it is. Jonathan, the part I just blocked off, if I have no mistake, with all the math I've had. If I look at this, you say, Professor, that's the same as black. I said, you sure? I have to multiply that mess out down there. And if it does agree with the black, I'm not gonna check it. But it should be the same as black. That's true, guys? Okay, so let's hope we don't have a mistake there. Now, I've got Anna watching me and Park watching me out for mistakes here. Guys, you okay with this? Looks good? Okay. Now, let's tie in some things here. Yeah, Eric, go for it.
Since you pulled out 2x plus 5 twice, does that mean the multiplicity of that factor is 2? Or
No, beautiful. Here we go, I'm gonna do it right now. Let's go through with what you see blocked off. For the x's, where the x's are located. 2x plus 5, I'm concerned about this too, right? 2x plus 5, guys, understood to be an exponent of 1 on the outside. That's odd, that's an odd number. X subtract 1, another factor, understood to be raised to the first. My last one, x plus 1 raised to the first. Now, tell me, are all those odd numbers?
Yes.
So when I finally start my graphing, and I split this up to see a little further, I'm gonna write down since Eric brought this up. I'm gonna set the 2x plus 5 equals 0, which I eventually would do anyway, and end up with a negative 5 halves. I'm gonna set the x minus 1 equals 0, you're gonna end up with 1. X plus 1 equals 0, you're gonna end up with negative 1. Can anyone tell me a word I could describe what did I just find?
your x-intercepts.
I found the x-intercepts. Also, did I find
Zeros.
where are the zeros? I just found the zeros, the answers to this. Now, do I have the time, or do you have the time to go back and plug in or replace up here the black, the x by each one of these numbers and do a check? I don't have the time, but they should check. Each one of these, take them back up here and replace x by negative 5 halves. Replace x by 1, negative 1. All of them should check. So we've got 3 zeros, 3 x-intercepts. And by the way, since those are x-intercepts, guys, I'm going to squeeze this in at the bottom. I think you'll be able to see it. I'm going to write it as negative 5 halves, 0, just to show it's an x-intercept. 1, 0, negative 1, 0. Those are my x-intercepts, and I've got my zeros staring at me also. Since I found this, Eric, you brought this to my mind here. Before I leave this, let's go and find the y-intercept.
Negative 10.
I got you. And y-intercept, he says, Professor, let's go back and find p of 0. Replace all those x's by 0. I'd go back up here and do that. All the x's would collapse and leave me a negative 10. Write this as 0, negative 10. Look at all the work required though, and I haven't sketched yet. Are we okay, guys? Now tell me, Eric would subscribe to this. Leo? Eric, help. On the outside of mine, all those factors is understood to be a 1, which is odd. So when I finally get to the sketch, I would assume that at this x-intercept, my graph is gonna cross. That means cross over the x-axis. Well, if this one also odd on the outside, it's factored, which tells me when I get to 1, it should cross again. And finally, when I get to, what was it, -1 on the end, if that's an odd number on the outside, it's going to cross again. Now, I don't have one up here yet, where there's something even. If this has been even, like a 2, had been x plus 1 squared, then what would happen at this point? It would touch. It would not cross over from one side to the other. Leo, go for it.
Can we look at the leading coefficients powered, like 4x cubed?
Oh, we're going to look at that. We're going to look at that.
When we look at that, can we also know if it's going to touch or cross?
No.
Or even?
Not necessarily. Not necessarily. Okay, guys? Now, I'm so glad he mentioned, he said, Professor, get ready to go to the sketch with all this little information you have on the board here. He says, is this playing a part from last week? He says, before I jump into it, Professor, seems like I remember something that we should focus on the first term.
Big parent function.
Is that the end, something like the parent function?
And
And
behavior.
the end behavior. So I mentioned end behavior over there, guys. So on the side here, let's see if I can do all this and make it look nice. On the side, let's go ahead and do this. Let's find the end behavior. And what was that question?
It's because when you do factoring for 2x squared minus 2, you put x minus 1 times x minus 1. That's the only thing, like. It's
Oh, it's
supposed
x
to,
minus 1, x plus 1.
yes, that's the only thing, like, I wanted to say,
yeah, here
that's
it is.
it.
So it's up here also.
Yes,
There you go.
that's it.
I put it down there. Glad you caught that. Now, end behavior, guys, we're gonna focus on that first term. What am I gonna do to that first term here? Well, let's go back and see, oh, I gotta find this. You can find these limits to see what's happening on the ends for the end behavior. We're gonna jump into this, guys, and find first the limit. Let's try as x gets large, x is approaching infinity, of my function, and we'll get an answer here shortly, and then we have to consider finding the limit as x is approaching negative infinity of my function. It's going to be something. If these two statements in the red, if I have written down correctly, if that doesn't tell a student that you're into an intense course, nothing will. Just those two short statements. The limit as x is approaching infinity, p of x. That says I'm in math class. And it's not algebra 1. That's not algebra 2. It's intense. It's getting intense. I'll see by the notation, it's getting intense. Now what am I going to do here? I'm going to go back and examine just the first term. Guys, I'm going to block that off. And watch carefully, I'm doing so much here. Just look at the first term, and here we go, guys. And this is something you can sort of think of. Translates, it says, please try a large number. X is approaching infinity means large. A large number. And Professor, what do you mean? Go back to here and replace X by some large number of my choice to see what's happening? No, it all just depends on the first term. That's sort of like a, what, parent graph you mentioned, okay? So guys, if I replace X by, right here, X by some large number, that's what this means, X is approaching infinity. If you put 1,000 in there, if I put 1,000 in there right there, and then I cube it, well, 1,000 cubed get even larger. Then times 4, even larger. So what might that tell me is the answer here for this limit?
Infinity.
It's approaching infinity. It's getting large also. The numbers are getting large. I'm making the x get large, and my result is getting large. Now, how about the other side? X is approaching negative infinity. Choose a number in your mind, negative something. Negative 50, negative 100, negative something. And you put it in here again. What happens if I take negative 50 and I put it in there and I cube it? Negative 50 times negative 50 times negative 50, is that pretty good size, but it's negative. Times 4, will that 4 change it? No, it's still negative. So what might the result be? Negative infinity. And I'll take into consideration that. I think, look at the board's full, just to get to one sketch. Now, does anyone see anything? I'm leaving out. Or are we ready? Okay, Eric, I got you in mind here.
I think we're ready.
Eric says, Professor, last week you showed us, which does work, you use sign analysis to see when is the graph below, when is the graph above. He says, maybe with all this new information, maybe I can avoid that. Or I may be able to bring it in by wish. So guys, let's see what this graph may look like with all that information given to me. Let's go to the grid here. I'm gonna pick up my x-intercepts first, guys. I'm going through all this information. X-intercepts in the green down there, if I have those written out correctly, is a negative 2.5. Let me go ahead and mark this so I can get ready for it. I'm gonna put negative 2.5 right there. Off between negative 2 and negative 3. I've got 1, 0. Everybody mark that right here. I've got negative 1, 0 right there. Now, I'm on top of the board there, so watch, guys. I'm writing so quickly. Do I have the x-intercepts? Okay. The y-intercept, since I'm here, is down here. It's a negative 10. So if you want to mark, make sure I get there. I think it's 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I will call it negative 10 down here. And mark that as my y-intercept. You get partial credit for all this. I don't have the graph yet, but at least got that. It might be wise, let's see, to get the end behavior out of the way. Go out on the ends and demonstrate the end behavior. Now this says x is approaching positive infinity. So go to that end on the positive side. Well, my end is right here on the positive side. Is that true, guys? That's furthest to the right. That's the end where I am. What's supposed to be happening as I go further? So it says make it go further. X approaching infinity, go beyond 1. What's going to happen to the graph out there? We said it's doing this. It's approaching infinity, which means it is going to be, with the right here, guys, doing something like this. I made a little curve to it. Let's go to the other end, which we described, if we have no mistake, this. So on the other end, negative means to the left. And to the left, guys, furthest to the left, my graph goes right now is this, negative 2.5. And what should be happening out there? It should be dropping. It should be going through negative infinity. You may say, Professor, or you say something like that, maybe? I am. And I made a little curve. They're not linear. It's not a linear equation. Now, Eric, Mr. Mathematician, here's for you. I'm not going to use the sign analysis. When I reach that x-intercept at negative 2.5, let me try to find on my board here where I am. Negative 2.5 is right here. I think we described this as it should cross.
Yeah.
Did we not say it's going to cross at all of them in this one?
Yeah.
So when I get to negative 2.5, I know, and I'm putting green, guys, to show this, it's going to cross over the x-axis. It's got to. That's what crossover means. Now, how high up is it going to go? I don't know. I don't know myself. Must have come back. Must have turned somewhere. There's a turning point. It turned somewhere because it's got to pick up that x-intercept there. That's another x-intercept. Now, what's supposed to happen to the next intercept? It's supposed to cross again. Now, this time I know when it crosses again, it's going to cross here. As it crosses, should it also pick up that negative 10 that's hanging on down there?
Yes.
Now, it may go directly to it, it may not. It may just drop down below, then come back up, who knows? It may do that, then come back up and pick it up. It's there, it's below. Crossed over. Finally, I'm going to reach my last x-intercept at 1. It's supposed to cross over again. Is that true, guys?
Mm-hmm.
In fact, will this graph here go up and connect to that x-intercept, which it has to do? Does that show it does cross over?
Yeah.
At that point? And there, I bet if I had Park to do an exact thing on a whatever device he has over there, we're pretty close to it right now. There's the graph. Now, Bart, any questions? Eric? there is a turning point right in here somewhere. Your textbook uses the word turning point, turning. And of course, point. There's a turning point. Down here, my graph turned somewhere in here. And this is described as a turning point. Does this turning point also look like it might be a local max?
Yeah.
And it is. Does this one look like it might be down here a local min? It is. It just so happens we can't find the value. I wish we could. The only two, me, probably three people in this room could find it. Those two over there and me, right? Anna, Bart, right? Was this, did you graph this one?
No. Should I grab it?
That should be pretty close to what the graph is, looks like. Okay, guys, there's the graph. Done. There.
So, I think the book described it as you have one less turning point than the
that's what I'm getting to.
polynomial. Is that universal?
That's what I'm getting to, universal. Now he says, Professor, this graph looks pretty nice here, and I should make it even look smoother. That shouldn't look like that, it should be more smooth like that. He said, Professor, I'm doing my homework, I'm looking at the book. Even though, Professor, your demonstrations are much better than the book. Right here? Very, that's great, yeah. But he's telling me, there's a way to see how many turning points you might expect even before you start graphing. Even before you do graphing. We have two here. And the rule says at most, you have the number of turning points to be one less than the degree, which is the highest exponent. So guys, the degree in this case was 3. And the rule is, they call it n minus 1. In my case, n is 3. 3 minus 1 tells me at most, you might get 2, and sure enough, we got 2 in this case. We got 2 turning points. So that will tell you how many turning points to expect even before you graph. So a little formula there, n minus 1, in my case, 3 minus 1. Guys, anything else on this one? Okay. The domain to range, I'm not gonna mess with this. Can someone tell me the domain expressed here for this graph, from left to right on the x-axis? Is it all reals? How about the up and down, the range? All reals. Nothing hard about this one. And there's the graph. Done. Yes, Leo.
So I saw that you got, like, all the way at the fully factored form, the px equals 2x total. How did you find out that there's, each one is to the first power, or how? Like, how would I?
Oh, you're gonna see here shortly. I got one coming up where there's an exponent of 2. Okay. Guys, anything else on this one? Now, if I ask you now, Jonathan, I remember you doing this. Please name an interval notation, since I have the graph. Where is p of x guaranteed to be positive? When is that happening? And we'll put it in interval notation. So right here, when is p of x this based on your graph? And guys, what would you look at on the graph to answer that fairly quickly? Where is it above the x-axis? So if I go to my graph, you'll say, Professor, this green part here is above the x-axis. Professor, this piece right here is above the x-axis. Now, can anyone describe for me the first one? When does that happen?
Open,
Open.
-5/2, comma -1.
-5/2 up to a -1, open.
Union,
And union, there's another one here.
1 to infinity.
Beautiful. U. There's the answer. Okay. And then we'll leave this one. Now, can someone in your own words tell me, after all this work up here, can anyone tell me, suppose I ask you at random to go back to the black and find P of, I'll give you a number. You're supposed to replace all those X's by that number. And I say, please replace X by 10. Now the question is, yeah, you're supposed to go back and place all those X's by 10 and crunch. But what am I guaranteed even before you crunch? Somebody tell me. That's That's why I love teaching math, you gotta know what it means.
A large positive number.
No, something else. Based on what we've just done, I'm not going to actually put 10 in there, you could. But what am I guaranteed, even before you do it, or you don't have to do it, what am I guaranteed if you put a 10 in there?
Positive number.
It's positive. 10's way out here, we've already said the graph's above the x-axis. It's above the x-axis out here. In fact, we described it as what? 1 through infinity. So put 25 in there, I'm not going to put 25 and crunch it out. That's going to be positive. Guarantee you, put 100 in there, it's going to be positive. Now, I'll give you a number between negative 5 halves, what was that, negative 2 1/2? How about negative 2? What should negative 2 give me? Also a positive answer? Yeah, that's what this means. That's all it means. Now, the last one here. P of x is, let's say, less than 0 this time. Less than or equal to. We can make it more easy. Now, let's see, where is it below? Okay, guys, let me try the black. My graph is below. This piece is below. Oh my goodness. This piece is below. All that's below. Now, can anyone in the black there describe for me, when does that happen? When is my graph below or on? Less than or equal to or on the x-axis. Well, this piece here is below, and right here it's on. Can someone tell me interval notation, when does that happen? Leo?
Negative infinity, open to, negative, 2 1/2.
Negative 5 halves, negative 2 1/2. Now, should I put a bracket on this time? Yes. And where else is it, below or on? All the screen. Now, I think that went from, I'll put a union here, went from, guys, what was that? Negative 2, was it?
Negative 1.
Or negative 1. Negative 1. Bracket out to 1, was it? I think. Is that true? Now we got the answers. How did you go wrong? I've always said, if you go wrong, sometimes I'll start writing on the students' papers. You went wrong. You went wrong. Okay. Anna, Park, can you think of anything else that may be, I'm leaving out that you mentioned about sketching a polynomial function? Okay, because that's what they have on their little quiz tomorrow. Just one for me to do. Little simple polynomial function, to sketch it, and name all the details here. Can't go wrong with this. Can't go wrong. Okay? Park, Anna, please tell me, will they eventually, when they move into that math 7 or math 8, might the instructor there say, okay, graph this like Ramsey did for you, but now I'm interested in this. I'm interested in that little region right there. That little cute little region. And what might they be asking down here when they look at that?
Find the area.
Find the area. Find the area. That's not a triangle. It's got some curve to it. That's not a triangle, 1/2 base times height. No, they're saying find the area of that one little section of that curve. Okay, I'll let that math 7 instructor do that for you. Leo?
Just curious, is that like the answer to your question?
No, we're not going there. That's not like campus do. Okay. Guys, any concerns here? Looks pretty good. Now, Leo, let me think. I thought, see if I did. And then we're gonna do a handout here. Oh, I did. Here we go. I'd like to sketch one more, guys. This one's in factored form to begin with. Then we'll jump into that handout. Let's call this part B. Let's sketch this one. Okay, P of x is equal to, and yes, I was asking about this, here goes, P of x in this case is equal to this. X squared, subtract 2, x squared plus 3. Mr. Park, I want you to go ahead and sketch that for me so we compare it to my sketch. And I finish, okay? Okay, guys. Now, geez, no factoring, this thing's factored for me, thinking there's no factoring to worry about here. Let's find the zeros, which corresponds to the x-intercepts. And guys, what's that mean? That means I'm gonna take these and split them up, set each factor equal to 0. This one equal to 0. This one equal to 0. Now, without me going through too much detail here, if I solve this, am I going to end up to 0?
Yes.
X squared is equal to 0, x is equal to 0. If I solve the next one, I see it's 2 looks like. Now, the last one's a little unusual. Anyone tell me what x squared plus 3 solved would be there?
Plus or minus I root 3.
Beautiful. That's exactly right. And you see shortly why I brought this in. Besides that square that Leo was concerned about. Guys, plus or minus I radical 3. Those are imaginary numbers. I can't place them on the grid. So I cannot use them as x-intercepts. They're having an effect on the shape of the graph, but I cannot use them as x-intercepts. So the only x-intercepts I can accept here are, right here, and here are my only 2 x-intercepts. I'm going to label those so I'll not forget them. So guys, down here for the x-intercepts, I have 2, 0, 0, and 2, 0. Only. Don't try to place an I on the grid. That's only for real numbers. Y-intercepts is at the zeros done, but the x-intercepts, y-intercept, we pick that up right here so we will not forget it. And to find it fairly quickly, let's find p of 0. If I go to try and replace all the x's by 0 here, this might, oh yeah, it's going to be easy. If I go back and replace all the x's by 0 and crunch it out, what's the answer?
0.
0. Yeah, 0 squared is 0 out front, everything collects. And of course you would expect 0, 0, because you got 0, 0 here. So the x-intercept, if 0, 0 is an x-intercept, automatically it's a y-intercept also. Now, step 2. Let me get this one out of the way here. Here we go. Yes, 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 yes. Leo, now go back to the original. I know right now, now we use a different color here, that those x-intercepts, those 2, 0, 0, 2, 0. 0, 0 came from here. I said x squared equals 0. Where the exponent is even. What does that tell me when I reach 0, 0 on the grid? Just one touch. Right here, guys, this is going to touch. Not cross over. At 2, 0, that came from x minus 2 raised to, and it should be a 1 first. That's an odd number. So it says when you reach this point, it should cross. This is still hanging on. It's having an effect on the shape, but I can't do anything with it. At least we can do imaginaries. So we've got all that. Let's get the end behavior out of the way and see what happens there. Gotta be careful on this. End behavior. So you're answering these 2 calc statements. The limit as you make x get large of this function. And on the other end, left, x is approaching negative infinity of this function. Guys, what does that depend upon? Back here, it depends upon that. The first term. This just depends on the shape of or information from the first term. Anyone tell me what's the first term of this polynomial function? And be careful. It's not multiplying out for you. That one was. So can anyone visualize if you multiply all this mess out and you just look at the first term? You don't expand all together. I see an x squared. I see an x. I see an x squared. What is that all together?
X to the
X to the fifth.
So
That's
you
what
don't
this
even-
will depend upon. Me looking at it. It's an X to the fifth. Now, let's see what's gonna happen. Easily done now. Find these limits, when you reach, math 7, it says replace X by a large number. So if I go in here and replace X by a large number and then raise it to the fifth, is it gonna get even larger?
Yep.
So here we go again. Implying enlarge infinity. Out on the other end, I'm replacing by a negative number. You take some negative number, raise it to the fifth, what happens? You still get negative. Some really small number. Negative infinity. And that might be, let's see if I have enough here. That might be enough to graph the thing. Let's see what happens, okay? Leo, you were concerned about that, I think, that touch part. When does it touch the graph? There we go. Now, very careful here. 0, 0, right here, is a 0, X is 0. Out 2, out here, is another x-intercept of 0. Y-intercept's not interesting, 0, 0. In behavior, out on the right, guys, don't get messed up here, is it supposed to be doing something like this? Out on the left, now on the left for me is 0. 0 is the furthest to the left, my graph is gone, but it's doing this. Is that the in behavior? Okay. Eric, I have not touched the sign analysis on these. Yes,
You're just going based off the end behavior off the limits, right?
right here.
Just to,
It says as you make x get large on the right,
Got it, but it will.
positive infinity, it goes up. On the negative side, it goes down. Eric?
The book doesn't put it in limit notation when they do this, but
No, I
if
would-
we do it
no.
on an exam, it's.
I don't know, I want you to get accustomed to the limit. That's what they do in math 7, okay? They describe it as ends approaching infinity or something like that. Okay. Guys, the graph's almost finished. Now I'm at 0, and we said at 0 right here, it should touch. I'm at 0 right now. Right here, 0, that's the x-intercept. So it says don't cross. Make the graph touch. Guys, the only way I can make it touch, that means it's going to do what? Bounce back. And when it bounces back, how far down it goes, I don't know, but it's gotta come back eventually and pick up that next x-intercept. And then at 2, did it actually cross over from the red to the blue? And we said earlier, at 2, it should cross. We described that even before we got to the graph. And stepping back, how cute, that's the graph. That's done. Mr. Park, that look pretty close?
Mhm.
Pretty close to what you had, right?
Mhm.
Yeah. Okay. Now, this was not too exciting. Please tell me, is that a turning point right there?
Yes.
Is it also a local max? Can you tell me, based on what you see up here, can you actually identify the value of this local max right now? Sometimes you can't do it because I could not do it over here on this one. Can I do it over there? The local max has a value of? 0. 0. Now, before I go any further, translation. You sit there all day and replace x by any number you wish. Replace x up here by any number you wish, Corey. Guarantee you, you'll get no answer. Hang on, where am I? Right here. We said what, there's a local max right here. Is it a local? In that particular locality, is that true? In that particular locality. The local max. That's a turning point. Hang on. Is there also a turning point here? Looks like it might be a local min, and this is one I can't find until you reach calculus. So we've got local max and local min. I was going to ask you or describe something else. I better hold on a second here. Not get carried away with this. Are you guys with me? So how many turning points did I end up with? What? 2 again? And I think, guys, did we end up with, what did we say? N minus 1? Hang on now, N minus 1. What was N in this case? What was the degree on this thing? 5. Hang on. What is the degree? Hang on. What is the degree 5? I didn't actually, where is it, guys? On the end, oh, right here it is. It was a 5, wasn't it? If I take that rule there, which is n minus 2, I put it over here somewhere, or n minus 1, was it? Was it n minus 1?
Yes.
Okay. That would leave me how many? 4. How many did we get?
2.
Is it the imaginary number?
It is.
extension of stuff?
It is. It is. And I'll make sure, is the rule say, does it say n minus 1 for the number of turning points?
Yes.
Mr. Park, is it n minus 1 if they want to find the number of turning points? Okay? It's not n minus 2, is it? It's n minus 1. Eric, it's n minus 1. So I got 5 here for my degree, and 5 minus 1 leaves 4. So there should be 4 turning points. But they describe at a max, you can have that many. You may not get all of them. Now, at a max number of turning points, I have only 2. What's messing me up that I cannot have 2 more?
Imaginary number.
The imaginaries that are going to come out when I actually ask you to find all, if I say find all the zeros, guys, not just the real zeros, I know this is a 0, this is a 0. Those are real. If I jump in here and say, hold on, Professor, oh, I did here. Those 2 are imaginary. Do I actually have 4 zeros here? Yeah. Which I should have, wait, 1, 2, okay, hang on. I got 0, 2, and these 2. So I got 4, don't I? What was the degree here? 5. I'm missing 1. Oh, I love this. I see 4 up here on the board, I'm missing 1, so let's get 5. Oh, Londa says, hold on, Professor. Where's the one I lost?
It's plus minus 0 for x squared equals 0.
Oh, right here?
Yeah.
Did that x equal 0, did it come from like an x squared? Guess what? That 0 is acting as 2 answers. It's like acting like a double. And how are we gonna write this so someone looking at my paper will realize that? When I write all the zeros, guys, all of them, I'm gonna write like this. We have, let's start with 0. Here we go now. It's going to show up twice because of this x squared. So they write this as 0 with a multiplicity, let me just abbreviate that word, of 2. 0 with a multiplicity of 2, that means 0, 0. So there's 2 of the zeros. Also, I got 2 itself, which is, shows up 1 time. I'll just write like that. Your textbook may call that multiplicity 1. And then those imaginaries, I got I radical 3 and a negative I radical 3. Now please tell me at this point, do I have 2, I guess 2, 3, 4, 5, do I have 5 zeros altogether now? And I'm supposed to have 5. Is all that making sense, guys? Okay. Woo! And the graph. And Mr. Parks tell me the graph looks pretty good, right?
Mm-hmm.
Guys, any concerns here? Yes.
Just clarity, so if I do find that I have 2 imaginary numbers, I should just automatically think, okay, take those away also from the amount of turning points. So
They are having an effect on the number of turning points, yes.
then I just look at it like the end behavior was still the x to the 5th of the when.
Absolutely, the end behavior has no effect on the end behavior. That's still x to the 5th. Jonathan?
So we would just graph the real zeros, which in this case are 0 and 2, and then from there we would just write, if it was, let's just say imaginary, we would just put that as the final solution set.
Yeah, especially if they ask you to list the zeros, and those are the x-intercepts. If they say, I use the word zeros here, more than likely they want just these 2 right here, but I just listed these as zeros like answers. These are the answers. So this is a full set of answers.
Got it.
Okay, I include the complex. But on the grid, you just show the real.
Got it.
That's the difference, yeah.
So just for example, there'll never be a time when you ask us to graph in imaginary.
No.
Got it.
No. Until you get to grad school. Okay. And it took me to finally get to grad school to realize two parallel lines intersecting. That was a shock to me. I'm not gonna tell you about that math, that was in grad school. Okay, so things can happen. Okay, guys, making sense? Okay, that's what we're doing here. Now, with that said, let's see if I did anything else here before I jump into with that handout. Ah, beautiful. Yes, here we go. And then that is going to apply to the handout. Guys, I hate to erase all this beautiful work. It's making all kinds of sense. I hope it's making sense to us, okay? But you walk into that Math 7 class, they assume you know that quickly. And of course, they're gonna start doing some calculus on this. They're not gonna wait for, you say, oh, Professor Ames gave me a lot of time. I found the zeros and I factored, and I did that and did that. No. They're gonna wait on you. Or should they? They're gonna ask you to do some calculus on this. Do some calculus on this, which will also lead you to the graph. The calculus. Guys, any concerns at all here? Okay, here goes. And this is where my little story is going to come in. On the side here, let me get the story out of the way first. If I gave you, before I start doing the rest of the notes here, a function like this, I'm calling f of x. And let's say it looks like this. A little story to lead you into where we're going. And I ask you to find the zeros. Every student in class could have an A in the class if that's your exam. Find the zeros. Here's the story. I used to be a supervisor of student teachers. And some of you guys may have had student teachers, those who were still in school, college, and they plan to be teachers. So what they do, if you plan to be a teacher, they send you out to the city schools, and you gotta do like an internship like thing with a teacher. And so then they sent me out to supervise the teacher and the student teacher. So I sat in the back to observe. And I was sitting in the back, and this particular math teacher was having a little bit of a problem with this one. Students weren't quiet, she was getting upset, and I was getting upset, and I was, oh, I don't know whether you should be a teacher or not. But anyway, so she was struggling, and she was teaching something like this. She didn't have F of X or P of X or whatever. She just had straightforward, solve this. And she had shown them factoring. How to factor, like I've shown you in here, how to factor and get the answers, which we could quickly do. She had not shown them quadratic formula. This was like a free algebra class, I think it was. They had never seen the quadratic formula. She was just doing factoring. And I was sitting in the back watching, and the students were trying. And the student sitting next to me, I would glance over at his paper to see what he was doing. I didn't quite understand what he's doing. He was not doing what we're accustomed to doing. He wasn't doing this. We would do this. Her class was doing this. She was teaching factoring. And then split that up and get the answers. Did I factor that correctly? I didn't make a mistake, did I? I got that. Is that correct? Yeah. Therefore, this kid next to me back there, took a long time. And so I kept on watching his stuff on his paper, and he finally, before he turned it in, he finally turned it in as this. Are those the zeros? Are those the answers? Yeah. But, he didn't do that. He couldn't factor. His factoring skills were not there. Quadratic formula, he had no idea, none of them knew the quadratic formula at that time. Now what on earth did that kid do? And I talked to the teacher after, she said, oh, he's weak, Brinkley. Yeah, I guess sort of sense that he's at work. No, sir, he's weak. He just cannot factor. Well, I said, have you got the answers though? And I said, could I talk to him? Sure, go talk to him. I talked to him. I said, how'd you get those answers? So he said, well, I'd share with me. Does anyone know how he could have gotten those answers and did not show the teacher factor?
He used Descartes rules.
No, Lord, he didn't know Descartes. Barely knew his name, he didn't know Descartes.
Did you look at the, constant?
Do it again.
Did you look at -6 constant?
He was desperate to get the answers. He said, sir, I was just looking at that constant term. I said, really? What'd you do with it? He said, I just thought in my head, what times 12 will give me -6? And I listed those numbers, like 1 and -6, -1, +6, 2, -3, -2, +3, I think those are the only pairs of numbers multiplied together, factors, and -6. I said, wow, okay, which is clever, you did. I said, how did you decide when you turned your paper in, it was these two of those pairs? What did he do? That's why he was taking so long back there. What did he do to finally decide to get these two, which did, sure enough, come out to be the ones she wanted? How did he get those? He plugged in each one of those. That's what he was doing back there on his paper. He was crunching out. He would plug in, Corey, you plugged in this right here, 1 into this. I said, oh no. 1 squared 1, subtract 1, that's 0. 0 subtract 6, that's a -6, so that's not gonna work. He plugged in the next one, -6, which got a little harder because larger number. And he plugged in these, plugged in these, plugged in these. Oh, finally. Those two worked. He just took the time to plug in each one. Had no idea how to factor, but got them to work out. Yeah, I thought, hold on. Where's my notes? I said, okay, that's clever. Which one's clever? You know, just try that constant term and test it. See what works. Then I asked him to do this for me. Oh, beautiful. Something like this. Now, that may even throw some of us in here. May throw me as a student, if I were a student. Okay, professor, same direction, she wants the answers, the zeros. And most of us would, and that algebra class was getting to this point where they could do it, they would factor. And you know, start 3x and 2x. Guys, I'm standing right on top of the board here. I'm trying to see if maybe a -5 goes here and a +2 here. Let me step back and see if it is. 4x -6, beautiful. The factors. And then we would say, solve this. You say, professor, it's this. Professor, it's this. And therefore, turn this in. And I have no mistake. Do you want us to do this right quickly with me? Are those the answers? Those are the zeros. Now, Jonathan, the kid was clever. Who knows what he did with his life after he left school? I don't know what he would have did, but he was clever. I said, okay, dude, you want to do this again? And he said, yeah, I'll do it again. What? Go down here and list all the factors of -10, like I did with -6. And he started listing these. 1 and -10, -1, +10, 2 and -5, -2, +5. I guess those are the only pairs for -10, isn't it? Right? And last time we did it was -6, and he went down and checked and checked and checked, plugged in, finally got it, smiled, the teacher smiled, I smiled, we're all smiling. He started testing these. I just sat back and watched. Knowing none of them worked. these are the answers. He could test all day. Those, none of those were checked. And he got frustrated. And I sort of smiled and I said, what's wrong? Your little system. He said, list all the factors, and I did exactly what you said to do. List all the factors of that constant term. Test, test, test. And nothing worked. And he got frustrated. I think he dropped out of school. I don't know. He got frustrated. What difference did I make here that threw it off?
Like a 6.
No. What did I do in my second one I asked him to do compared to the first one? First one, it looks something like this, which his method works perfectly. Then I asked him to do this one, it did not work. So what threw his system off in the second one? The leading coefficient. In the first one, the leading coefficient of what? 1. His system works every time. If I throw a different number in front for the leading coefficient, I throw, what was it in this case, a 6 was it? It will not work. Now that leads me right into what we're going to do on this handout. Leads me right into where I need to go on this handout. You'll see why that little story may have helped us when we get to this handout here. Guys, I'm watching my time. We've got 15 minutes, which will take me right into where I want to go. Jonathan, let me check my notes first. See if I'm ready for it. Oh, hang on. Of course. Here we go. Before I jump directly into it, the board's full here. If we do it right quickly, then we'll jump into the handout. We're going to do a little reading. Oh, by the way, as I erase, can anyone tell me, where am I? Oh, here. Something that maybe he could have done, and he was clever. I've met many students who are just clever. They're just clever, and some who are just out there brilliant. But many students are just clever, which I love.